This first question is from Achieve Homework 6, number 30, and it asks us to draw the product formed from the condensation of three molecules of the monomer glycolic acid, and it gives us one molecule of glycolic acid, and it asks us to draw two more molecules and to join them together. So the first thing I'm going to do is I'm going to look at my molecule over here. And I'm going to try and identify what kind of functional groups I have, because I know that if we are going to be forming a polymer from a monomer, there is going to be some sort of reaction happening between the functional groups of the molecule, right? So let's try and identify the functional groups in glycolic acid. And so we can see that over here, we have a carboxylic acid, and we can see that over here, we have an alcohol. So, what reaction do we know that involves the addition of a carboxylic acid with an alcohol? So, a reaction that you guys have probably learned of is a what's called a Fischer esterification. And the general form of this reaction is you take your carboxylic acid. So, I'm just going to name a general carboxylic acid. Um, So you have your um, um, carboxylic acid like this, and then you would add an alcohol, so your OH group bounded to some sort of other R group, and then typically you need some sort of acid catalyst to get this reaction to happen. So we can use H2SO4, and then from there your products would be one, an ester, so you would get your ester formed, and then you would also get a water molecule. And so basically, in this reaction, you can see that we have water as a side product. So that also lines up with what this question is asking, which is like asking for, which is a condensation reaction. So typically with a condensation reaction, you would have H2O as a product, or like a byproduct in this case. Okay, so as you can see in this reaction, we have water as a byproduct, and so that makes sense with what this question is asking with the condensation part, because condensation means that you have H2O leave as a byproduct in your reaction. So this lines up with the Fischer esterification mechanism that is happening over here. So. Another thing to keep in mind for this mechanism is that you might be wondering like which hydrogens and oxygen ends up leaving as H2O in your final molecule. And so the answer to that is that it ends up being the O and the H from the carboxylic acid and the hydrogen from the alcohol. So these three atoms over here that are boxed in blue end up becoming your water molecule in the product. Okay, so now that we have gone over the general mechanism of a Fischer esterification, or like what the general reactants and products are, now we're going to approach this question. And so first I'm going to show you the shortcut, which is you don't need to know the exact arrow pushing mechanism of how the esterification mechanism works. You can still get to the answer, but after that, I will explain and draw out the mechanism in case you want to look at that in more detail. So the shortcut way to do this, or to identify the polymer, is first I would draw out three molecules of glycolic acid. So if I have one molecule over here, and I'm just going to draw out the skeletal structure. I'm going to draw our second monomer, and then I'm going to draw out our third monomer. Okay, so now that we have our three monomers, we have to remember that what we're forming as a product is that we're going to be forming an ester and then also water. So the condensing part is we're combining two monomers to form an ester, and then we're going to have water as a byproduct. So if we're combining three monomers, we're going to have two connection points. So we're going to have two molecules of water leave. So now I'm going to draw a box around where the molecules of water will leave. And so remember I said that over here, your OH from your carboxylic acid and your H from your alcohol are what form your water molecules. So if I draw that same box around here, these two molecules, like this, these atoms will become water, and these atoms will become water. So if I redraw this molecule um, at the end of like what it would look like if I were to um, remove these water molecules, you would keep the structure of the molecule the exact same, except now I'm going to skip over this blue box and I'm going to instead go straight to drawing where, this oxygen. So now I formed an ester. And then I'm going to keep going. So I have 1, 2 carbon. So 1, 2. And then I have my double bond. And then I'm going to um, go again. And then I skip these atoms. And then I go straight to the oxygen. And then I draw my oxygen. And then I have 1, 2 carbons. So 1, 2. And then I draw my CO double bond, and then I draw my OH. And so this is the answer of what it would look like if you had to combine three molecules of the monomer glycolic acid to form the polymer that the question was asking for. And now I'm going to show the mechanism of what it would look like to combine these two molecules, just in case you're still a bit confused about like how do you know it's these two, like these three atoms that form the water molecule in the end, and it's not like the other oxygen from the alcohol and things like that. And so it'll make a lot more sense if you see the mechanism. And so now that you can see like the general shortcut of the mechanism. I'm going to go over the arrow pushing. So remember, you're going to have your carboxylic acid, you're going to add an alcohol to it, and you're going to have some sort of acid catalyst. And so in this case, because our one molecule has both the carboxylic acid and an alcohol, one molecule of it is going to act as like our carboxylic acid, and we're just going to have another molecule act as like our alcohol. And so if I redraw that down here, and let's say I have some sort of acid catalyst. So typically, like you can just write your acid catalyst as like HB. This can be any acid catalyst. It's like it's generic. And the first step is going to be protonation of the carbonyl oxygen. And so the lone pair on the oxygen is going to attack the hydrogen. This double bond is going to push off onto the base over there. And then you are going to get this molecule. And so this molecule now we have our what's called an activated carbonyl. And so we have basically activated our molecule to be more likely to participate in a nucleophilic attack, which is going to be our next step. And so our next step is that we're going to have our nucleophile come in. And so in this case, this is going to be our alcohol. So I'm going to draw in another molecule of glycolic acid, because remember, like if you imagine we're going to have like multiple of these molecules, right? And so in the first one, we're just going to be using the carboxylic acid part, but in the second one, we're going to be using the alcohol part. And so this is just our second molecule of glycolic acid. And if you remember, let's think about nucleophile, electrophile again. So our oxygen has a lone pair of electrons, and so this molecule is going to be our nucleophile because it has like electrons that are available to attack, and then This carbon over here is our electrophile because if we remember CO double bonds are polar, meaning that the oxygen is more electronegative than the carbon, so the electrons will be pulled towards the oxygen, leaving behind a partial positive charge on the carbon. And so now we have our nucleophile can attack our electrophile like this. And so if we draw our product from this, we get this molecule, which is, oh yes, and also I'm gonna erase these to make it less crowded. But when this oxygen attacks the carbonyl carbon, the one of the double bonds will get pushed off onto the oxygen like this. And so then you would get an OH and you would have like no charge on that because you moved the double bond to act as a, like a lone pair. And then we're gonna redraw our OH here. And then now we have this second monomer attached. And now we have a positive charge on the oxygen because we just made a new bond. So now that we have this molecule, what's going to happen next is a proton transfer. So oxygens, as we have seen in this step, right? And in this step, oxygens can be protonated and they can be deprotonated. So any oxygen has a lone pair available can pick up a hydrogen and it would then like have a positive charge, right? And so what's going to happen in this case is a proton transfer. So this oxygen over here has a lone pair, right? And what can happen is that I'm going to draw this in blue. This oxygen this oxygen's lone pair can attack this hydrogen, push off this double bond towards this oxygen. And now what we get is the exact same molecule, except we have basically moved the location of the positive charge of like where the positive charge on the oxygen is located by moving the location of the hydrogen. Okay, so now that that has occurred, um, if similar to other mechanisms that you have seen like earlier in the course, if you have um, if you have a positive oxygen that is bonded to two hydrogens, we know that this is a really good leaving group because this molecule can leave as water. And so what happens next is this bond will break apart, will attach to the oxygen, and we'll have H2O leave. That's where like the condensation part of this reaction comes from. And then because that bond will leave, we're gonna have to make up for it. So what's gonna happen is we're gonna reform our carbonyl double bond that was in our original molecule. So this lone pair on this oxygen will then push down towards here, and then we get this molecule. So we have now we're getting close to this looks really close to what our final product was. The only thing now is that we have to deprotonate our protonated carbonyl oxygen. So then we can take our base. This is just a typical base in your solution because remember you had an acid catalyst earlier in the reaction, and that'll just do a deprotonation over here. And then you get your final product of when you combine two monomers of glycolic acid. And so then if you wanted to add a third molecule, you would just do the exact same mechanism again, and you would just add a like exact same mechanism and you would just like make the chain longer and longer. So this is how the mechanism works. So again, to go over the steps. So this first step is the protonation of the carbonyl oxygen. And the purpose of this step is that you are activating this carbonyl oxygen to be more reactive towards nucleophilic reactions, which is going to be the next step. So the second step over here is a nucleophilic attack. of that carbonyl carbon, which is the most electrophilic site. And it's going to be attacked by the alcohol on the other molecule because the oxygen lone pair um, on that um, the lone pair on that oxygen of that alcohol would be your most nucleophilic site, and which will do the attacking. Our third step over here is going to be a proton transfer because again, any oxygen that has a lone pair available, it can it can like pick up a hydrogen, it can be protonated, it can be deprotonated. It's a reversible reaction, it can go back and forth. So our oxygen over here can be protonated, but it can also be deprotonated. And this OH group over here is right now not protonated, but it can be protonated because these are all just like reversible reactions. And so once that proton transfer happens, we get to our next step, which is H2O leaves. So again, if you have oxygen with a positive charge and you have two hydrogens as shown over here, H2O is a very good leaving group. Oxygen is not happy with the positive charge. It is much more stable and happy as a water molecule, and so that's why H2O is able to leave. And then your final step is deprotonation, where you have your base, which is will be in solution as a result of your like acid catalyst. So like I forgot to draw it over here, but like you would also like have on the side, you would have your like the conjugate base of whatever that acid was. But yeah, so you can like bring that base in, and that can like deprotonate your protonated carbonyl oxygen for you to get your product. And then you would have your side products, which would be HB, which would regenerate your acid catalyst. And so that is how a Fischer esterification reaction works. That is how you would combine monomers of glycolic acid to form a polymer. It's a condensation reaction because you form water as a side product. And that is it for this question. Moving on to this next question. So this is from practice exam 3. It's question number 5. And it says in organic nomenclature, the functional groups are given priority in the following order: lowest priority first, highest priority listed last. And then it asks you to circle which of these priority rankings is correct, with lowest being on the left and highest being on the right. So this is a mnemonic I use to try and remember the ranking of the functional groups. It's not perfect, but it covers most of the functional groups that you need to know typically. And so um, the mnemonic is chemists, chemist, enthusiasts are, and then in need of a kilo of alcohol after each day. And um, so this is the mnemonic. So chemist enthusiasts are in need of a kilo of alcohol after each day. And so you would look at the first letter, so CEANAKAA, and then all three letters of day. And so the C stands for carboxylic acids, which are this functional group, which should be the highest. So I'm gonna erase this and I'm gonna put this is the highest and this is the lowest. Okay. The E stands for esters. So esters look like this. The A stands for amides. So amides, you have your carbonyl group and then you have a nitrogen attached to it. And then N stands for nitriles. So you have your C triple bonded to an N. And then the A stands for aldehydes. And so you have your carbonyl CO group, and then you have that bonded to a hydrogen. The K stands for ketone. The A in alcohol, coincidentally, it is alcohol. So that one's easy to remember. That's the alcohol functional group. And then A, the last A stands for amine. And then amines look like this. And so there are also some that are not covered in the list. So like for example, acid halides are inserted right here. And so acid halides, which are CO groups, carbonyl groups bounded to a chlorine. And then thiols are lower priority than alcohols, but higher priority than amines. So SH groups. Um, I like to remember that they're paired near alcohols because like alcohols and thiols are very similar functional groups. And then you just have to remember that alcohols are higher priority than thiols. And then for day, I remember that D stands for like double, which is like double bonds, which are alkenes. So alkenes. And then A is alkane, so single bonds. And then Y stands for the Y in alkyne, so it's triple bonds. Um, and then those are all going to be the lowest priority. And then the IUPAC rule naming has like changed, I think, in like the past like recent years. But typically like alkenes, alkanes, alkynes, those are all lowest priority. Um, and then something to remember are there are some functional groups where they do not have a parent name suffix. They are only prefixes. And so those groups are halides. So if you have like a functional group that's like with an X, so like for example, like chlorine, bromine, etc. And then you have alkoxides, which are like if you have like your methoxy groups, ethoxy groups, and then also nitro groups. Which is if you have an NO2 group. So these three groups over here, they only have prefixes. They do not have a parent functional group name. So they will not be included in your like priority naming for like the parent name at all. And so looking at our options provided, if we first look at A, we see if we want lowest on the left and highest on the right, we have alcohols and alkenes, and immediately I know that's wrong because alcohols are higher priority than alkenes. And then the second one is alkenes, alcohols, ketones, aldehydes, carboxylic acids. That looks right to me. Now I'm just going to double check the other ones to make sure those are not right. So I see alcohol, ketones, aldehydes, carboxylic acids, alkenes. Alkenes are not higher priority than carboxylic acids. Carboxylic acids are the highest priority, so I know option C is wrong. And then if I look at the last one, it says alkenes, alcohols, aldehydes, ketones, and carboxylic acids. Now, this one is really close to being right, except it has aldehydes and ketones switched around. So, um, actually aldehydes are going to be higher priority than ketones. And so D is wrong, C is wrong, A is wrong. So the correct answer in this question is B. So nomenclature priority is something that you just have to memorize. This mnemonic helps me kind of memorize the general framework of what the order of the functional groups are. It's not perfect. You have to like add in your acid halides, your thiols, and you also have to remember which functional groups exist on your prefixes. But it gives you a good general idea of like functional groups that of like what the order is for priority. So, this next question is from practice exam 3. It's question number 10. So, it gives us four different molecules and it asks which of these is or are the product of a condensation reaction. And it says to circle all that apply. So, what is a condensation reaction? So I went over earlier in the first problem, I went over like one example of a condensation reaction, right? Which was a Fischer esterification. So I'll redraw out like the general mechanism again. So if you have a carboxylic acid and then you combine that with an alcohol, you have sort of some sort of acid catalyst, you get a ester and you get water as a side product. So remember, condensation reaction means that you're forming some sort of smaller molecule, such as like water as a side product. So in this case, you're forming water. And again, the water comes from the OH group on the carboxylic acid and the hydrogen on the alcohol. And so, what are some other condensation reactions that you might have come across in lecture? Another one is the condensation of amides. So, this is a reaction that's typically used when you want to synthesize amides, which is remember, a CO group bonded to a nitrogen. And so the reaction mechanism for this one is you can start with a carboxylic acid, and instead of reacting it with an alcohol, you can react it with an amine, such as, let's say, NH3. And then when you react this, you get um, your amide. And then you also get water as your side product. And so the water in this case also comes from the OH group on your carboxylic acid and the one of the hydrogens attached to the NH3 group. And so both of these are examples of condensation reactions. They form water as a side product. And so now I know that like, okay, um, we're trying to see of these four molecules, which of them could have possibly been the product of a condensation reaction. So I know that, okay, if I have water as a side product, there are like two different molecules I can have. I can have an ester, which is a carbonyl bonded to an oxygen bonded to another R group, or I can have an amide, which is a carbonyl group bonded to a nitrogen, and then the nitrogen can be either bonded to R groups or hydrogens. If I look at these molecules over here, which ones do I see are an ester? So I can see this second one is an ester. So I can say like, oh yeah, this molecule has the possibility of being formed by a condensation reaction. And then I can also look at these four molecules and see, okay, or any of these like amides, because I know that you can form an amide and also have water be a byproduct. And so I can see this fourth molecule right over here is an amide. You have the carbonyl CO group bonded to a nitrogen. And so these two molecules can be the product of a condensation reaction. So now I'm going to look at the other two. And so the other one is an ether. So do we know of any reactions, of any mechanisms that can form an ether that are condensation reactions? Yes, we do. Another reaction that you learned was acid catalyzed dehydration. And so the way this works is, let's say you have an alcohol of some sort, and then you add an acid, so like let's say like H3O plus. Um, Basically what you can do is you can form an ether like that. And if we assume like that. And so um it also produces water as a side product. So this is also an example of a condensation reaction. And so we know that, yes, this first one can also be the product of condensation reaction. And now we just have to look at this last one. So this last molecule has an aldehyde functional group. And so now we have to ask, is it possible to form an aldehyde from a condensation reaction? Now, technically, yes, it is possible to form an aldehyde functional group from a condensation reaction. And I don't believe you covered this reaction in lecture, but it's called an aldol condensation reaction. And um, the acid catalyzed version will produce H2O as a byproduct. But unique thing about aldyl condensation reactions is that it requires you to have an alpha beta unsaturated aldehyde. What does this mean? That means that wherever your aldehyde is formed, um, on the beta carbon, there needs to be a double bond. So if this is your alpha carbon, we call the carbon that is bounded to the oxygen or your carbonyl carbon, the alpha carbon, and then the next carbon over would then be your beta carbon. And so there needs to be a double bond over there. Um, and so in order for it to be the product of an aldyl condensation reaction, I'm not going to go over the mechanism for an aldyl condensation reaction because I don't believe you need to know it. But if you go through the mechanism, you'll see why you need like that second double bond to form. So because this molecule had an aldehyde group, but it did not have that double bond that was like attached to the beta carbon. It's not the product of an aldyl condensation reaction, and therefore it's not the product of a condensation reaction. Um, and that is not like how the aldehyde was formed. And so that's why the answer to this question is only the first, second, and third molecule. So the way to solve this question is I would suggest first to identify your functional groups, right? Because you can see that your first molecule has an ether, then you have an ester, then you have an aldehyde, then you have an amide, right? And so, um, the important thing about that is that it helps you kind of think about like, okay, what are some reactions that I know that like create an ether, create an ester, create an aldehyde, etc. And that can help you kind of think like, okay, so now that I know what reactions can make these molecules, what are the byproducts of these reactions? Is water a byproduct of this reaction? If yes, then that means it's a condensation reaction. If not, that means it's not a condensation reaction, and I wouldn't circle it as an answer choice for this problem. And so um, I would start, so now that you are starting to learn about like more and more reactions and it's getting harder and harder to remember all of them, my suggestion would be to try and categorize them into functional groups. So which functional groups are part of your reactants, which functional groups are part of your products, etc. And that can help you better remember your reactions when you have so many of them, right? Now, the next question is question um, is a question also from practice exam 3. It's question 11C, so part of the reaction mechanisms. And it asks us to predict the product of reacting this amine with 2 molar equivalents of bromopropane in NaOH aqueous. So now, what is this reaction? So we're reacting an amine with 2 bromopropane. So yeah, like 2 molar equivalents, sure. Um, we have 2 molar equivalents of bromo to bromopropane. And so And so if I see an amine and then I also see a an alkane with some sort of like halogen attached to it, like a bromine, I know that this is going to be an alkylation of amines reaction. And so typically alkylation of amines, their reaction follows two steps. So the first step is an SN2 reaction, and then the second step is an acid-base reaction. And these are both reactions that you've learned before. And so what's nice about like these reactions, like when you get into like amines and when you get into like all these like other functional groups, is that typically they are just a combination of reactions that you already know. And so it's kind of like building on your knowledge of like mechanisms that you like already have in your like toolbox. And so now I'm going um to predict the product, I'm going to like draw out the mechanism for like how this reaction would work. So I'm going to draw out my starting amine. So NH. Okay. So you have to remember that nitrogen, um, and like typically like in amines, like nitrogens have a lone pair attached to them. So nitrogens will typically have like three substituents. So you can have like two hydrogens and like an alkyl group, and then you'll also have a lone pair. So the first step is going to be an SN2 reaction. And so this lone pair on our nitrogen is, so this is going to be a nucleophile. And then again, a bromine is has like is electronegative. And so there's going to be a partial negative charge on the bromine, a partial positive charge on the carbon that it's attached to. And so that's going to make that carbon electrophilic. And so our nucleophile attacks our electrophile. And then um, we get a molecule that looks like this, where we still have our nitrogen bonded to the two hydrogens, but now we have this group attached to it. And I forgot to draw this, but in an SN2 reaction, when your nucleophile attacks your electrophile, which is your carbon, it kicks off the bromine. Um, aka a substitution reaction. And so now you get like this intermediate, and now your nitrogen will have a positive charge because you have four substituents on it. And if you calculate the formal charge, you have a positive charge on the nitrogen. So now the thing to remember is that in this reaction, um, you have NaOH. So what is NaOH? NaOH will dissociate into Na plus and OH minus. Why is that useful? That's useful because what can happen is that we can have our OH act as a nucleophile. It can deprotonate um, our ammonium like salts, and then we get this molecule over here. So now we have our nitrogen is no longer protonated, so now it's in like amine again, and it has a lone pair. Now, what do we know if we have a lone pair available? If we have a lone pair available, we have a nucleophile available, and it can do another round of this exact same reaction. And so you're also like hinted at this in the problem when it says that you're given two molar equivalents of two bromopropane. So we used one of them right here. So now we're going to use our second equivalent of um, two bromopropane. And now it's going to be the exact same process as before. So our nucleophile is going to be our amine, and specifically we're going to start our arrow from the lone pair on the nitrogen, and it's going to attack our carbon on the bromine, carbon attached to the bromine, and it's going to push off those electrons that like bond to the bromine. And then if we draw the next step, we get this molecule for here. And then our nitrogen will also like have a positive charge. And then If we remember, we have a lot of OH minus in solution. And so what's going to happen is a deprotonation step. So our lone pair on the oxygen is going to grab this hydrogen and it's going to push this bond onto the nitrogen. And then our final product will be a nitrogen that has these two like these two 3 carbon groups attached to it along with the original group that it had. So this will be your final product of this reaction. So going back again, alkylation of amines, we have 2 steps. We have our SN2 reaction happening, which we can see like in this first step over here. And then we have our second step, which is our acid-base reaction, which is going to be our deprotonation of the amine from like when it's now like has a positive charge. And that's this step over here. And we make the acid-base reaction happen using the OH minus that we have from like the NaOH that's like added in solution. Now, the thing to remember about amines is that the only reason why we were able to pass this second step, um, or the reason why we were able to pass the second step over here is because we had OH minus to deprotonate the hydrogen and then allow us to have a lone pair available on the nitrogen to then do another nucleophilic attack, right? So let's say we didn't have this base available. So if this base was not available, then we wouldn't be able to deprotonate the nitrogen, right? And so if we're not able to deprotonate the nitrogen, then we no longer have a lone pair available on the nitrogen, meaning that we're not able to perform another round of this reaction. So you would just like stop the product over here with your salt, right? So it's important to like think about like the mechanism, especially when it comes to amines, to think about like, are you in acidic conditions or are you in basic conditions? Because if you're in acidic conditions, then your nitrogen is going to be protonated at the end. But if you're in basic conditions, then you're able to like run your reaction like forward and you're able to do another round and you're able to like get this like final product with where you're able to add like 2 moles of 2-bromopropane. And so that is how you do this question. Another thing to note about alkylation of amines, this is just a small detail about like how alkylations of amines work, is that as you increase the like substitution of your amine, that makes it more nucleophilic because of the um, electron donating alkyl groups. So the second round of this reaction is faster than the first round of this reaction because your nitrogen now has 2 alkyl groups attached to it. And what that means is that like alkyl groups are electron donating, meaning that they like donate electrons. And so if we're now donating electrons to the center nitrogen, we're making it more nucleophilic. We're making it have more of a like minus like charge, and so that's going to make it a stronger nucleophile in the reactions moving forward, and that makes it react faster. So that is just a trend that you should be thinking about when it comes to like alkylations of amines, like as you go through multiple rounds of adding alkyl groups to an amine, and like the reason why behind increased substitution of an amine would increase its nucleophilicity. Okay. So the next question is from also practice exam 3. It's question 11D. And now it asks us to predict the reactant, so our starting product, and it starting reactant, and it gives us the product of the reaction. And so I see that we're adding something with NaOH. We're also adding heat, and then we get an alkoxide So or not an alkoxide. Sorry. We get an Okay, sorry, yes, I was right. So we get a carboxylate ion. And a carboxylate is just like the name of this molecule over here. Like if you have like let's say like a carboxylic acid and just have like an O minus group instead of like, let's say like an OH. And then you also have an amine. And so I can see that like some sort of like breaking apart happened. And so now I'm trying to think like, okay, what reactions do I know form a carboxylate ion and an amine? So, a reaction that you might have learned what is hydrolysis of amides. And so, in this case, this reaction, since we have NaOH, we remember that NaOH dissociates into Na plus and OH minus. And so this is done under basic conditions. And so, note that this reaction can also be done under acidic conditions too. But since the reaction gives us one of the reactants being NaOH, we know that we're adding a base. And so we are doing this hydrolysis under basic conditions. Okay, so now I'm going to draw out like the general reaction mechanism for like a generic hydrolysis of amide reaction. So if you have an amide, I'm just gonna draw a generic one. Let's like if you had like an R group here and like you had another R group here. And then the reactants in this reaction are NaOH, H2O, and heat. The products of this reaction are going to be your carboxylate ion. Na plus is a spectator ion, so typically you wouldn't draw that, but you can draw that in if you would like. And then you would also get your amine. And now I'm going to draw, um, so like that's like the typical like generic reaction of what a hydrolysis of an amide looks like. And so if you see that your products have a carboxylate ion and like an amine, and you also see that your reactants are like, oh, you have NaOH, you have heat. Typically like NaOH would also be done like with water, so it's aqueous. You know that you can put into context like, oh, we're doing hydrolysis of an amide reaction. That probably means that my starting molecule has to be an amide. And so now I'm going to um, draw out what like this reaction mechanism would look like for this example. So this is not the problem. The same like starting amide as the problem. This is just like a generic amide. And so this can help like make it easier to like put into context like what how you would think about like how do you go backwards from like if you have a product, like how do you figure out what the reactant is? And so the mechanism for this reaction is first of all, you'd have your amide, and then remember NaOH dissociates into Na plus and OH minus. And so your OH minus, the oxygen, would attack the carbonyl carbon, and then it would push off um, the one of these bonds to make a lone parent oxygen. So then you would get O minus on here, and then you would have a nitrogen bonded to your two R groups still. And then you would also have an OH bonded here. The next step is going to be an elimination reaction. And um, see, I accidentally drew an extra carbon here, so I'm going to redraw that. Would be an elimination reaction. And so your lone pair from your oxygen will push in, and then your nitrogen group would now leave. And so what this would do is you'd reform this CO double bond. You would have your OH group, and now you would also have your N group bonded to your two R groups. But now remember, there's two lone pairs on this nitrogen, right? Because there's like an implied lone pair that I didn't draw in here. It's like it's in there, but now that we pushed off that double bond, you have another lone pair. And so now this nitrogen will have a minus charge on it. And so, um, nitrogen doesn't like having a minus charge. And so what will end up happening in this reaction is one of the lone pairs will rip off the hydrogen from this OH group, pushing off this lone pair onto here. And so then that's how you get your carboxylate ion, and then you get your amine. And the reason why um, you get like so you might be like wondering like why do you how do you know if you have like the hydrogen on the OH versus on the N, right? Because like it's like a reversible reaction. It can like go back and forth like um stuff like that. Um the reason why the minus charge ends up being on the oxygen is that this carbonyl is much better at stabilizing a negative charge compared to a nitrogen atom. So in general, oxygen is electronegative, and so electronegative atoms are better able to stabilize negative charges. Um, the second reason is that you have like the carbonyl oxygen too, so this carboxylate ion has resonance, and the amine doesn't, and so a nitrogen in the amine is like not as able to stabilize the negative charge as well as the oxygen on this like carboxylic acid is, and so. That is why you end up with a carboxyl ion instead of an amine with a minus charge. And so, again, to review the steps, the first step is an addition reaction. You're adding the OH minus group to your carbonyl. The second step is an elimination. You're making your amine group leave. And then your third step is deprotonation. Okay? And so that's how you end up with your products being a carboxylate ion and an amine. So the next step, um, so now that you understand like the generic like mechanism for like how the hydrolysis of amines of sorry, hydrolysis of amides work, now the question will be like how do you work backwards, right? And so I'm going to shift this downward so that I can have make room to draw out the mechanism in the problem. Okay, so of course, something you can do is you can just make up a starting product and you can just trial and error starting from that starting product to get to the final product by like moving the reaction forward. But I think that it is good practice to try and learn how to work reactions backwards. And so let's start from our product, so our carboxylate ion and our amine. So, if we think back to the mechanism I just showed you, the final step was this deprotonation step, right? And in this deprotonation step, that's where we get our carboxyl ion. So before the hydrogen was attached to the oxygen, but now it's attached to the amine. So let's now do the reverse of that. So what if we were to do the reverse of that? So I'm going to draw a backwards arrow to show like where that came from. Um, so I'm going to redraw um, this hydrogen to be more explicit. Um, so I'm just gonna draw like out where they came from. So this hydrogen used to be attached to this oxygen. And so now if I redraw that out, I get HO attached here, and then I can redraw my molecule, and then I would have my amine has a hydrogen attached to it, but now it has a minus charge. And so if I remember, this is my deprotonation step. And then what was my step before the deprotonation? Well, before the deprotonation was the elimination step, right? And what was I eliminating? I was removing the amine group that used to be attached to the carbonyl carbon. And so now I'm just going to draw, hey, what if I'm going to draw out like this nitrogen to be attached to the carbonyl oxygen again. And so if we remember what that looks like, we have to push the electrons off of the oxygen. And so this oxygen is going to have a minus charge, and that basically makes room to add the amine group back on, right? And so this second step was elimination. And so now what was the step before elimination? Well, the step before elimination was addition, right? And um, before addition, um, like what were we adding to the molecule? If you remember, we were adding OH, right? We're adding OH minus. And so, oh look, I have an OH minus right here. So I have to, what was the step before that OH was added? Well, that was the amide, right? I had a CO double bond bonded to my amine. And so now I'm going to redraw that without the OH. And so you would just have your CO double bonded to that. And then you would have your amine group. And so in this case, since it's directly bonded to the CO group, we call it an amide, but um, it used to be your amine. And so this molecule um, is what your starting product would be. So hopefully you can kind of see how I tried to work backwards um, from um, like the hydrolysis reaction. Um, the easiest way to like break down reactions, I think, is to like try and like break down like try to think like what are you doing in each step? Like, am I adding something? Am I eliminating something? Am I like deprotonating or protonating a molecule, etc. And that kind of helps you like remember what is like the next step. And so in this case, I was able to work backwards of the hydrolysis of an amide reaction. And I was able to get to the starting product, which is this. And if I wanted to check my work, I can rerun through the forward arrow pushing mechanism of this reaction. And if I were to do that, I would get the same final product in my answer. Um, and yeah. Now, something to note um, about like reactions involving amines. So, this is not relevant to the question, but it is something to think about. So, let's take these as like my products, right? Um, and so like let's say I wanted to like why would you want to perform a hydrolysis of an amide, right? Um, it might be like in an experiment or like when you're performing like a synthesis reaction, your goal might be to make a carboxylic acid, right? Um, like you're trying to make a carboxylic acid and you have an amide and like look, you're getting really close, right? You have this like CO double bond, it's bonded to an oxygen. Now the only problem is that it has a minus charge instead of a hydrogen, right? Um, And like, so how are you supposed to fix that, right? So typically what we do in an experiment or like in the synthesis reaction, it's called an acid workup step. So your second step in the reaction would be, so like your first step, if you started from like an amide, right, would be to add heat, NaOH, H2O. Your second step would be to add acid. It would be to add something like H3O plus, because when you add acid, you can protonate this carboxylate ion to become a carboxylic acid, right? And there, now we have our carboxylic acid. Now, what happens to this amine? We can't forget about the amine. So what happens to the amine? Well, you have to remember the amine has a lone pair on it. And so what do pairs do if you're around an acid? A lone pair will act as a nucleophile, like it will become protonated, right? So if you have an amine and it's in the presence of acid, it will become protonated. And so you won't have, like, this molecule won't stay the same if you add the acid workup step. So I'm going to write down this is your acid workup step. Um, you would actually have a salt form. So you would have your exact same group, like exact same amine, except now it's just going to have another hydrogen attached to it. And it's going to have a positive charge. So it's like you formed a salt. And so you formed your carboxylic acid, and now you have a salt. And so typically, like in these reactions, forming the carboxylate ion is like an intermediate step before you form your final carboxylic acid. And so you would add like H3O plus, and you would have your final carboxylic acid. Now you might so yes, that is the important thing to remember about amines. Amines can be in their protonated state or deprotonated state, and what matters is trying to think about, like, are you in acidic conditions or are you in basic conditions, and thinking about like um, when you would be in a protonated state versus not. Okay. So the next question is from discussion section week 6. It's question 1D. And it asks you to draw the molecule from a given IUPAC name. And so it asks you to draw 4-oxo, 3-propyl cyclohexane carbaldehyde. And so um, it's a pretty long name, but I first start out these kinds of problems by looking for where is the parent chain, right? And so I can see this over here, cyclohexane carbaldehyde. So carb carbaldehyde means that you have some sort of ring, like let's just say this is a ring, and then attached directly to the ring, you have an aldehyde group. That's what the carbaldehyde suffix means. Cyclohexane, so this prefix hex means six, ane is an alkane, so we have 6C, it's an alkane, and it's cyclic. So I'm going to draw out 6 carbons in a cyclic form. It's all single bond, it's an alkane. And if I combine it with the carbaldehyde, where I need to have an aldehyde group directly attached to the ring, I'm just going to draw on an aldehyde group attached to the ring. Now I'm going to number my carbons. And so because your aldehyde group is your parent group, that's going to be your number 1 carbon. And so then I'm just going to number around my carbons in a circle. And so 3-propyl. So propyl is a group of 3 carbons. And so on the third carbon, I'm going to draw 3 carbons sticking out of it. So 1, 2, 3. So that's my propyl group. 4 has an oxo, and so oxo is the prefix for a ketone. And so on carbon 4, I'm going to draw a ketone group. And so this is going to be 4-oxo, 3-propyl, cyclohexane carbaldehyde. So the next question is discussion section week 6, question number 3. It's about physical properties, and it asks us to rank the solubility of these species in water. So it asks us to make 2 lists. So we're ranking A through D separately from E through H. And so now let's look at now let's think about in general, like, solubility in water. So what are the properties of water? So water is polar. So if high solubility will equal polar molecules. So if you think about molecules that like have H bonding, polar, et cetera, et cetera. And then low solubility would be non-polar molecules. Um, and that's because they wouldn't interact with the water. And so you can think about like the phrase like dissolves like. And so if something is going to be soluble in water, it's going to be interacting with the water molecules. How will you be interacting with the molecules? Well, you'll interact with the water molecules if you have similar properties to the water molecules. So if you're polar, then you will interact with the water molecules, therefore increasing your solubility. So now that we have like that general like rule of thumb laid out, so we're gonna look at our first list over here, which is A through D. So A, we have propane. So I'm gonna draw out propane. So propane has three carbons, and so then propanone or acetone looks like this. Pentanol. The pent is five C's, so 1, 2, 3, 4, 5. And then on the first carbon, you'll have an aldehyde. That's what the Al suffix means. And then propanol, um, you would have three C's, and then you would have an OH group on the first carbon. So, what do I see about these molecules? Well, first of all, I know that my highest solubility molecules will be ones that can participate in H bonding with water. And um, so now let's think about which ones would those be. So propane is nonpolar. So there's no H bonding. There's no even like polar interactions, right? It's a completely nonpolar molecule. Um, Acetone can accept H bonds. So if you imagine like a water molecule like um, this oxygen can interact with the hydrogen that's attached to this OH. Um, and like a CO group is also kind of polar. So like the oxygen has a partial negative charge. And so it's like has some sort of polarity going for it. Um, so the CO group is also polar. And pentanol can also accept H bonds. And so you can imagine if you had like a water molecule, um, the oxygen can interact with the hydrogen of the water. And then you have propanol. And so propanol can participate in H bonding, can accept H bonds, it can donate H bonds, it has the OH group, the hydrogen is directly attached to the oxygen. And so therefore, um, if we rank from most soluble to least, you would have propanol would be the most soluble, and the least would be um, propane because it's nonpolar. And so now you have to decide between these two middle molecules over here. And so the way you decide that now is through like how many carbons you have. So if you remember that if you have longer chains that are non-polar, so like if you have these really long non-polar chains, you're going to be less soluble in water because it'll interrupt like the like dissolves like that's just solving that's happening with water. And so therefore, because acetone has less carbons than pentanol, it's going to be more soluble. And so we're going to write here that acetone is the second, and then pentanol is the third. So that's the first list for A through D. Now let's think about the list E through F. And so hexane has six carbons. And then we have pentanone, which has five carbons. And you have a ketone on the carbon there. Pentane dioic acid. So you're going to have five carbons. And then on the two ending carbons, you're gonna have um, um, carboxylic acids. And then your last molecule is gonna be hexanol, and you're gonna have six carbons. And then you're gonna have an OH group. And so if we think about properties again, so hexane is nonpolar. Pentanone has an oxygen, so it's slightly polar. It can accept H bonds. Hexanol, similar to propanol in the one we just talked about, can like do H bonding. And then pentadioic acid can just has more like OH groups, so it can just do more H bonding. So when you think about most soluble to least, the answers for this one are going to be the most soluble is pentadioic acid. The second is going to be hexanol. The third is going to be pentanone. And the fourth is going to be hexane. And so the reasoning for that is that like these two can do H bonding. This one, the pentadioic acid, can just do more H bonding. Pentanone is at least polar and it can accept H bonds, and hexane is nonpolar. So it wouldn't interact with the water at all. And so that is how you would rank the physical properties when it comes to ranking solubility. So again, when it comes to ranking solubility, and you're trying to be soluble in water, you have to think about like, okay, because water is polar, we're trying to look for polar molecules because polar molecules will dissolve in water, and versus non-polar molecules will not be soluble in water. So the next question is discussion worksheet, is discussion section, week 6, question number 4. It also asks about physical properties. This time we're comparing the boiling points of these two different lists of molecules. And so we're comparing these four with each other and these four with each other. So I'm going to look at this list first. And so when we think about boiling point, right, what makes a higher boiling point? So if you have increased strength of intermolecular forces, so those are like the forces like in between molecules. So like think about like H bonding and think about like dipole like London dispersion forces, etc. would equal a higher boiling point. This is because if your molecules are held together more strongly via intermolecular forces, that means that you're going to have to put in more energy to break them apart, to boil boil your mixture. So that means that if you have to put in more energy to break those bonds apart, you're going to have to do that in the form of like heat, right? Heat is one way to do that. And so you're gonna have to increase the temperature. So increased strength of intermolecular forces would mean that you would have an increase in boiling point. Okay. So now we look at this first list. So I'm going to draw out what these molecules would look like. And so 2,5-dimethyl-3-hexanone would look like this. So on carbon 3, I have a ketone, and carbons 2 and 5, I have methyl groups. Okay, so this is 2,5-dimethyl 3-hexanone. And then one octanol is going to be 8 carbons with an OH at the end. So 1, 2, 3, 4, 5, 6, 7, 8. And then you have an OH at the end. Then you have nonane, which is 9 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you have octanol, which is 8 carbons with a aldehyde at the end. So 1, 2, 3, 4, 5, 6, 7, 8. And then you have your aldehyde. Okay. So now you have to think about which ones will have like the strongest intermolecular forces. And so like typically like the ranking would be like, okay, if you have H bonding, and then if you have like polar interactions, and then if you only have like London dispersion forces, which are like just like dipole-dipole interactions, right? And so and like LDF forces that typically comes like if you have like non-polar molecules, right? And so like those are typically like the weakest. And so if we think about what has the um strongest interactions, that would be the ones with H bonding. So this has um octanol. Octanol has an OH group, so this has H bonding, right? And then this one, this molecule is just um is slightly polar. This is non-polar. This molecule is non-polar. And then octanol also is has the carbonyl carbon, so it is also polar. And so now, so octanol has 8 carbons, and then if I count how many carbons the first molecule has, it has 1, 2, 3, 4, 5, 6, 7, 8. So it has also 8 carbons. Okay, so if we think about like which one has the highest BP, that one is pretty straightforward. There's only one molecule that has H bonding. It's oct one octanol. So that has the highest. If we think about the lowest one, which one has the weaker intermolecular forces, it's a molecule that's nonpolar, and so that's going to be nonane. And so now we have to look at between our two polar molecules, how do we differentiate between like these two, right? And so the key thing to think about here is branching. So if your molecule has more branching, you're gonna have a lower BP. And the reason for this is that if you have branching that interrupts like your forces, like your intermolecular forces that are between your like different atoms, like the atoms like across like different molecules is going to be weaker or like disrupted because of like the branching structures. And so increase in branching means a lower boiling point. And so because these molecules have the exact same number of carbons, we're not going by molecular weight here, we're going by branching. And so therefore, octanol will have a higher boiling point than 2,5-dimethyl 3-hexanone. So that is the answer for the ranking of highest lowest boiling point for the first list. Now, if we look at the second list, um, so 2,5-dimethyl 3-hexanone. So same molecule in the first part of this question. It looks like this. And then we have our second molecule is 1-octanol. So also same molecule in that question. So 1, 2, 3, 4, 5, 6, 7, 8. And then you have an OH group. Then you have heptane, which is an alkane of 7 carbons. So 1, 2, 3, 4, 5, 6, 7. And then you have nanoic acid. So nanoic acid would look like 9 carbons with a carboxylic acid attached to the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And you have a carboxylic acid attached to the end. And so let's look at the properties of each of these molecules. So 2,5-dimethyl 3-hexanone is polar. We know that from the carbonyl oxygen. There's a partial negative charge on the oxygen, partial positive charge on the carbon. 1-octanol has that OH group, so it can participate in H bonding. Heptane is nonpolar, and anoic acid can also participate in H bonding, and it also has that polar CO bond, right? So you have a partial negative here, partial positive here. And um, so we can pretty easily compare like the bottom two, right? So if we have highest BP, lowest BP. Our lowest BP is going to be heptane because you only have nonpolar interactions. Our second lowest is going to be 2,5 um, dimethyl 3-hexanone because it only has polar interactions. But now, like, how do we compare like the two molecules that have both have H bonding? So it turns out nonoic acid is going to be higher because the reason why is that you basically remember that this other oxygen site can also act as an H bond acceptor. Meaning that when you have like a bunch of these molecules together, this ketone oxygen, or sorry, this carbonyl oxygen can also accept H bonds too. Not only like the like OH group over there. And so it just has like another site and it's also overall like more polar too because that's CO bond, etc. And so therefore it would have the strongest intermolecular forces, making it have the highest boiling point. So nonoic acid would be the highest. And then the second highest would be 1-octanol. And so that would be your ranking um for letters E through H for highest boiling point to lowest boiling point. Okay. So the next question is discussion section, week 7, question number 4. And it asks you to list, to label each of these molecules as an acetal or hemiacetal, and then identify the carbonyl starting material that produced these molecules in acidic ethanol. So, um, the first part, which is labeling them as a hemiacetal or acetal, is um, um, it's basically the way you do it is you look at the molecule and you see, look at the carbon that's attached to two oxygens. So if you have a carbon and it's attached to oxygens that are attached to R groups, so attached to like carbon groups, that's going to be a hemiacetal. Sorry, an acetal. If you have a carbon that's attached to two O groups and one of them is an R group and one of them is an H, that is a hemiacetal. So going down this list, the first molecule, your center carbon, it's attached to an OR group and it's also attached to an OH. Therefore, it's a hemiacetal. This second molecule, if you look at this carbon that's attached to two oxygens, you have an O attached to an R group and an OH. Therefore, it's a hemiacetal. This third molecule, you have your center carbon. It's attached to there's an OR group, and then there's another um, oxygen attached to an R group, or like the R group being some carbons. Therefore, it's an acetal. And then same thing in this last molecule, you have an OR group and another OR group. Therefore, it's an acetal. And so that's how you can pretty quickly identify if a molecule is an acetal or hemiacetal. Just look at a carbon that's attached to two oxygens and then look at to see if those oxygens are attached to a hydrogen or if they are attached to an R group, the R group being any amount of carbons. So then you have to identify the carbonyl starting material that produced each of these molecules in acidic ethanol. Okay, so the way I'm going to do this question is first I'm going to for one of the hemiacetals, so for this second one, I'm going to tell you what the answer is, and I'm going to show you like the forward step of like that's like how the hemiacetal reaction would work moving forward, just so that you know the general mechanism of a hemiacetal reaction. And then I'm going to show you how you can actually work backwards, starting from the hemiacetal to get to your starting reactant. So for this second molecule, we have this. So OH here, then you have O here. And um, this problem also tells you that these molecules, like these hemiacetals or acetals, are being produced in acidic ethanol. So acidic ethanol basically means that you have ethanol and then you also have H3O plus, so some sort of acid catalyst. And the way this mechanism would work is that So first I'm going to just tell you what the starting product is for this one. So in this case, it was propanol. And so propanol looks like this. So three carbons and you have an aldehyde attached to it. So how does a hemiacetal reaction, like how do you get to the hemiacetal, right? And so we're going to be reacting this with H3O plus, and we're also going to be reacting with ethanol. And ethanol is like based off of what the problem told us, right? And so the first step is going to be like activation of the carbonyl, right? So the oxygen has a lone pair and it's going to be protonated by the acid. And so this oxygen's lone pair is going to attack the hydrogen um, and then it's going to be protonated. So now we have an oxygen with a positive charge. Um, and then we also have our ethanol still here. And then we also have like water, right? Because the water was generated as like a side product based off of like this group, right? Okay. The next step would be a nucleophilic attack of the carbonyl carbon. So remember, oxygens have a lone pair. They act as our nucleophile. Remember, CO double bonds, they're polar. So there's a partial positive charge on that like carbon that's attached to that oxygen. And so this lone pair is going to attack that carbon. And so now we are going to get this intermediate. I'm going to keep drawing that H in. So we have this oxygen. It's bonded to an H, and you also have your like two carbons over there. And then also like this double bond would push off to the oxygen too. So then you would have OH. Um, okay, and so now you have like a neutral molecule, mostly except for a positive charge on this oxygen over here. Now you have to remember that in this reaction you have water. So water can um, turn into H3O plus. So again, it can deprotonate the oxygen, so it's a reversible reaction. So this lone pair will come in, rip off the hydrogen, push the double bond onto here, and then you get your neutral intermediate, which is this, right? And so then remember, like I just said, oxygens with lone pairs can be protonated and deprotonated. And so now that we regenerated your H3O plus, this other oxygen over here on the bottom can come in and get protonated. And so now you have a similar molecule to before, except you basically moved. You can think about it as like you moved where the positive charge was through like this deprotonation, protonation, etc. And so now you have a positive charge over here. Okay. So the next step in this reaction is um, is going to be okay, so I actually realized I took you one step further than you had to go. So actually, if you stop right here, this is your hemiacetal intermediate. So you have your carbon and it's attached to an OR group and it's also attached to an OH group. And so that is the formation of your hemiacetal. And so um and so that is the formation of your hemiacetal. And so you can see that, okay, where did this OR group come from? This OR group came from ethanol, right? And then the way you got to this like OH group over here, it used to be a CO double bond. And so the way you get the way you get like the oxygen, like the hemiacetal to get like two oxygens attached to a carbonyl, like, attached to a carbon is that you must have started with the CO double bond. So like if you look at this forward reaction, you can kind of try and like put together like where's their starting material, how did that end up in your like intermediate? And so now knowing this forward mechanism, I'm going to show you how to work backwards from the for the first problem. So if we take this example, I'm going to redraw it on another page. So we're trying to figure out how this um, hemiacetal was formed, right? So first, I identify my carbonyl carbon. Sorry, I identify the carbon that's like attached to two oxygens, and I know that it will be the carbonyl carbon. Um, and the reason I know that is because from the mechanism, the way that you get two oxygens attached to the same carbon in this step right here is because the double bond is there. And so I know that, okay, in order to get to this, I must have had in my starting product like a double bond, like somewhere over here, right? And so the next thing to think about is, okay, which group was on the original starting molecule? Was it the OH or was it this O with like the two carbons? You have to remember that we're adding this in acidic ethanol. And what was my nucleophile in this second step over here? It was the ethanol, right? So my starting group was um my starting group was like the OH and then like the um was an oxygen was like an aldehyde and then you had the alcohol come in and attack in a later step. So therefore I know that okay, this over here was not here before. This is part of the ethanol, right? And I know that this hydrogen is comes from like from the protonation step. And then um so now I know, okay, I keep the molecule the exact same, except now when I get to this blue carbon over here, now instead I'm going to draw a double bond and then I'm going to draw my hydrogen that's going to be attached there still. Because remember, there's still a hydrogen attached here. And so this would be my starting molecule. And then you can do the forward mechanism. You can go from this starting molecule to try and get to the hemiacetal if you want to like verify or prove to yourself that this is correct. But that is how you can work backwards. And the way I was able to work backwards was I was able to work backwards by walking through the forward mechanism of hemiacetal formation and thinking about like where did my oxygens come from? Where did like the hydrogens come from? Etc. And trying to like piece together like the different steps, the different like um, nucleophilic attacks, deprotonation steps, etc. So now if I were to do the third molecule, which is an acetal, it looks like this, right? And so I am going to be so we're adding acidic ethanol, so which is H3O plus, and your ethanol, which looks like that. Okay. So hemiacetal is a bit different from acetal formation. The reason for that being um like involved like in the mechanism. So similar to what I did with the first set of two, I'm just gonna tell you what the starting product is for this first one. So just so you can see the forward mechanism, and then I'm going to work backwards for the second one. And so the starting product for to form this acetal is 2-butanone. So it looks like this. And so the way the mechanism works is so first you have your H3O plus, So same as last time, your oxygen is going to get protonated. Um, and so then you're going to get this. And then this makes your carbonyl carbon more activated towards nucleophilic attack by your ethanol. And so then we're going to have your ethanol come in. It's going to attack this carbon over here, push this double bond off, and then you're going to form this. Right? Okay. So the next thing that is going to happen is is going to be um like a hydride shift, proton transfer, whatever. It's similar to last time. This is just like a bunch of acid base steps. Um I already showed it in like the previous mechanism, so I'm just gonna like fast forward a bit to like where you would um get like the like neutral form. So you could get OH um and then O. So this would be your hemiacetal, right? And so um now so like I'm just gonna make a note like there's like acid base steps for like protonation, deprotonation. So now the thing about like oxygens, remember they can be protonated, deprotonated, etc. So now that you have your like H3O plus here, this oxygen can now attack hydrogen over here. And so when that becomes protonated, we have an oxygen that's positive attached to two hydrogens. And what do we know about that kind of molecule? It can leave as water. It's a really good leaving group. So when that molecule leaves, in its place, another ethanol molecule can attack. And so then we have this molecule over here, and we like have water as a side product. And then at the same time, we also have like if we just perform the same um, like acid-base steps where the oxygen can like deprotonate that hydrogen, then we get our um, acetal intermediate um, product. So like that is how like the forward mechanism works, how you go from a ketone to an acetal. So now I'm going to show you the how you would know how to like work backwards. And so for the last part of the question, it gives you this acetal molecule, right? And then you're trying to figure out like how do you get to that? And so I look first for my carbon that is going to be my that is attached to like the two oxygens because I know that's where my carbonyl carbon is going to be. And I know that this group over here is going to come from um this over here, like this our ethanol molecule. And I know this group over here is also going to come from our like ethanol molecule, right? And so, but I also know that when you have a like acetal like form, how do you have an ethanol attack that carbon? It needs to be electrophilic in some way. How do you have an electrophilic carbon? It needs to be a CO, a double bond. And so I know that that blue carbon has to have a CO bond. And so I would have a CO. And so this would be my starting product over here. And so that is how you are really easily and quickly able to identify like what is your starting product. Um, like that would form like the hemiacetal and acetal. It can like be really quick. Like I can just like as I've shown you right here, but to like understand like the why behind it, it really helps to walk through the forward mechanism of the reaction to see like how like the arrow pushing works and to see like where the atoms come from and how they rearrange themselves. So the next question is achieve homework 5, question number 15. It says that both aldehydes and ketones contain carbonyl groups. In aldehydes, the carbonyl carbon atom is bonded to a hydrogen atom, whereas in ketones, the carbonyl carbon is bonded to another carbon atom. And it asks you to select the true statements about aldehydes and ketones. So the first statement is ketones with fewer than 5 carbon atoms are soluble in organic solvents, but not in water. So this statement is false. So actually, if you have small ketones, they are soluble in H2O. So this is because so ketones we know are polar, right? You have like a dipole moment here, so the oxygen has a partial negative charge. You have a partial positive charge, the carbon, and that can like interact with the water molecules, right? So it's a competition between like the polar interactions versus the London dispersion forces of the nonpolar part of the molecule, right? And so that's why like if you have a really short carbon chain, the polarity like kind of outweighs the London dispersion forces of like the non-polarness of the molecule, which is why you are soluble in H2O versus like if you had a super super long chain, it's not. And so that is why the first statement is false. The second statement is ethanol has a higher boiling point than ethane. So ethanol um, looks like this. So it's an aldehyde with 2 carbons versus ethane is just 2 carbons. And so what do you know about higher boiling points? So increase intermolecular forces strength equals increase boiling point. And so this molecule, this ethanol is polar. This ethane is nonpolar. Therefore, polar equals stronger intermolecular forces equals higher boiling point. Therefore, this second statement is correct. It's true. The third statement is propanol is a gas at room temperature, whereas formaldehyde is a liquid at room temperature. So let's take a look at what these molecules look like. So formaldehyde looks like this, and propanol looks like this. And so the question is stating that formaldehyde is a liquid and propanol is a gas. So like looking at these molecules, right? How do we know if something is going to be a liquid or a gas at like room temperature? So like typically like it can be hard to like kind of guess, but like when you're comparing two molecules, you can see like similar to like boiling point, right? If you have stronger intermolecular forces, then you know that you're going to have like a higher boiling point, right? And so I know that like when comparing formaldehyde and propanol that like, hey, if this molecule has like stronger intermolecular forces, it's probably going to take more energy for it to be like a gas compared to a liquid. So propanol has stronger intermolecular forces, right? And so I would expect that propanol, like if you have the same temperature, propanol, since it has stronger intermolecular forces, because it has 3 carbons, right? So that's like more London dispersion forces, right? Um, it's gonna be like it's gonna be more likely to be a liquid than a gas compared to formaldehyde. So actually compared to like so more LDF means like dipole-dipole interactions. So actually if you like look it up, formaldehyde is actually a gas at room temperature while propanol is a liquid. So this question is false because the reverse is actually true. Um, and you might think like, oh, how are you supposed to know that? It can be kind of hard to guess, but like at least when comparing these two molecules, if you look at like the intermolecular forces, you can kind of make a guess to see like, okay, if you have stronger intermolecular forces, you're probably going to be at like a solid or a liquid state compared to like a gas state if you're like comparing it with another molecule at the same temperature. Okay. And then the next statement states that both aldehydes and ketones can hydrogen bond with water. That is correct because they are both polar molecules. They can hydrogen bond with water. They are both like H bond acceptors. So that's true. Ketones have lower boiling points than hydrocarbons of similar sizes. So this is false because Ketones are actually polar. So what do we know about boiling point? So increase IMF equals increase boiling point. So hydrocarbons are nonpolar, ketones equal polar. So which equals increase IMF, which equals increased boiling point. So this is actually false. The opposite is true. Ketones have a higher boiling point than hydrocarbons of a similar size. And last one is ketones are polar molecules. Yes, this is true. If you look at a ketone and you look at the electronegativity values of oxygen compared to carbon, oxygen is more electronegative. Therefore, you have a partial negative charge on oxygen and a partial positive charge on the carbon. So three of these statements are true, three of them are false. Okay. The next question here is achieve homework number 5, question 20. And so it asks us to draw the alcohol that is oxidized to give the product shown and to show the hydrogen atoms. So I'm just going to draw the line structure just so it's easier to look at. So I have 5 carbons here. So 1, 2, 3, 4, 5. And then I have an aldehyde. And then on carbons 2 and 1, 2, 3, and 4, I have a methyl group. Okay, so um, to draw the alcohol that is oxidized to give the product shown, the key thing about this is that you keep the same number of carbons. Everything about this molecule is the exact same. The only difference is that instead of an aldehyde, you would have an alcohol. And so all you got to do is draw the same molecule and you keep the same number of carbons. So I'm going to count them just so I'm sure I don't miss a carbon. So 1, 2, 3, 4, 5 in my main chain. So 1, 2, 3, 4, 5. And then I have my 2 methyl groups. And then I'm just going to draw an alcohol off of that first carbon. And so this question also in Achieve, it specifically asks you to show all the hydrogen atoms. And so if you need to do that, you can do H3C, CH3, um, CH3, OH. So you can draw like your H's here. So you can like just draw all your hydrogens in from your question. So 1, 2, 3, 4, 5. And so yes, this would be your answer of what the molecule that would be oxidized to form that aldehyde. So the next question is achieve homework number 5, question number 23. It says cinnamaldehyde is the main component of the essential oil that gives cinnamon its flavor and scent, and it's oxidized in the body to form cinnamic acid. And so it asks you to first draw cinnamic acid. And so the problem tells us that it's oxidized, so the aldehyde is oxidized. So all we got to do is oxidize this aldehyde. And so um, when we oxidize aldehydes, what functional group do we get? We get a carboxylic acid. And so you would just draw the same molecule, except now you would have a carboxylic acid. So that is what the molecule would look like. And then we have to identify the systemic name. And so first you have to identify so the parent group is going to be your aldehyde. So we know that the ending suffix is going to be oic acid. And we know that the parent chain is 1, 2, 3 carbons long. So it's going to be and then since there's an alkene on carbon 2, it's propanoic acid. And since the alkene is on carbon 2, it's going to be 2-propanoic acid. And then on carbon 3, we have a phenyl group. This is a phenyl group, so 3-phenyl, 2-propanoic acid. So this would be our answer. And that is it for the problems I have to review for exam 3.